Okay. All right, testing. Is my mic picking? Where's my mic? Yes. There it is, good.
Okay.
Go to the other device, start. All right, we're going to wait another minute or two, but in the meantime, if you want to download the Mathematica file, diffraction by a circle, we're going to make a little bit of use of that today. All right, let's get started. So we've been talking about diffraction by a number of different systems. Now we're going to talk about diffraction by a circle because that's the shape of most lenses. So we already know that we can overcome spherical aberration either if the lens is a Cartesian oval or if we have a narrow numerical aperture. But light's a wave, and so it's going to spread out, and we're going to get light at more points than just here, which the lens is designed to focus it to. We want to get as little light as possible out here, or at least we want to get most of the light to be really close to this point. So we want to figure out what the edge of the light distribution is. We're going to have some peak around here, and that's going to get weaker and weaker. We know that from all the other systems we studied. And it's going to be 0 if we have destructive interference. And so we want to figure out how far off would we have to go to get destructive interference. Now, there are many, many paths, not just coming from the top and bottom of the lens and points in between, but coming from points out of the page, all right? So it's a much more complicated shape than we've done before. But the largest possible path difference would be the path difference between a point or a path that goes from the top of the lens to here and the path that goes from the bottom of the lens to here. Now, drawing both of those paths and these two on the same diagram is complicated. So what we're going to do is we're going to measure this path length and this path length relative to these two, because these two paths take the same amount of time, all right? These two paths go, or are parts of paths that go from object point to image point. And we know that all paths from object point to image point take the same amount of time, so everything arrives in phase. So if I want to measure the length of this one, or more importantly, the difference between this length and this length, that's the same as measuring the difference between this length and this length, or the amount of time along any other path. So that's going to be, if this is y, and this is theta, theta is the angle that we use to determine the numerical aperture. This path difference here is going to be y sine theta, because this is theta, so this is 90 minus theta, so this is theta. And then this path difference is opposite theta, y is the hypotenuse, so y sine theta. So this one is shorter by y sine theta. Meanwhile, this one is longer by y sine theta. So the difference between those two will be 2y sine theta, because you got y sine theta minus negative y sine theta. And that's the difference between the extremes. Now, if we made the difference between the extremes lambda over 2n, well then lambda over n is the wavelength in whatever medium we've got on the right, then, okay, we'd have destructive interference between this path and this path, but all of the other paths would differ from each other by something less than lambda over 2n, because those are the two largest possible extremes. And so all of those others are going to differ by less than half a cycle. They're not going to interfere destructively. And now I'm just going to invoke a fact that we could get from an integral that I'll do a little bit later, maybe. But even if I do that integral, it involves invoking some facts about special functions. So it's a fact that we just kind of have to take for granted. If we make the largest possible path difference, not lambda over 2n, but 1.2 lambda over n, so 1.2 wavelengths in that medium, then the average path difference is lambda over 2n. Right? And what that means is if we go out to here, then at this distance y from the center, 2y sine theta equals 1.2 lambda over n, or y is 0.6 lambda over n sine theta, or 0.6 lambda over the numerical aperture. That's how far from focus you can go if we have a diffraction limited lens before you get a 0 of intensity. Any questions? Now, it's important to make clear that we're making a big assumption here. We're making the assumption that all of the paths from object point to image point take the same amount of time. We are assuming that this lens obeys Fermat's principle. So we're assuming no aberrations. As soon as you have aberrations, then some of these paths take different amounts of time. And that introduces additional phase shifts that we haven't accounted for here. So this is only an ideal case. And this ideal case where you get something called the Airy disk, because you've got a circle of radius 0.6 lambda over NA, that is the best possible case. And so Zmax gives you the option of showing the Airy disk to know how far off you are from the ideal. Let's switch to the Mathematica file. We can play with it. In the first command, I've defined something called the Airy point spread function, where the Airy point spread function has a 0 where we predicted, but more importantly, it everywhere in between this peak and this 0, it follows a very particular kind of curve called a Bessel function. We can play with that. We can fix the wavelength. So we fix the value of k. we can change the diameter of the lens. And as we change the diameter of the lens, we can see that this changes, that this width changes. If we go from looking at the focal plane to looking at diffraction pattern as a function of angle, we'll get to that in a little bit. We can also compare it with a Gaussian curve, a curve of the form e to the minus x squared, basically, or e to the minus y squared times some constants. We can see that if we pick just the right value of one of those constants, then this exact shape, for the ideal case, matches pretty well with the Gaussian. And e to the minus y squared is a lot easier to work with than Bessel functions. So most of the time, people in practice work with e to the minus y squared as an approximation. And we'll get back to that in a little bit. We'll pull some data from Zmax and do a comparison. All right, so let's talk a little more about those curves that you made on the last Zmax assignment. Here we graph spot size versus aperture diameter. As we change the aperture diameter, we're changing the numerical aperture in that denominator. So for a while, we're making the spot size smaller. But then at some point, as we widen the aperture, now we've got a whole lot of paths taking different amounts of time. It's fine if the diffraction limit is a good approximation if the paths take almost the same amount of time. But once they start taking substantially different amounts of time, then we get ray diagrams that look more like that in Zmax. Then we can't use the type of wave theory we've been doing. We have to do much more complicated calculations. The symptom of this is that if you look at the area, if you look at the spot diagram, when it's very narrow, all of the spots fall inside the Airy disk, assuming it's focused. That's your sign that it's diffraction limited. Because if you think of doing two different kinds of calculations, one with just rays ignoring wave behavior, one with a simplified wave theory that ignores, that pretends that all the paths to the image point took the same time. This is the prediction of the simple wave theory. This is the prediction of the geometrical ray theory. The geometrical ray theory is the overly optimistic prediction here, which means that the real limitation is diffraction. Once we get out to here, once we have a larger aperture, then the what we call the Airy theory, Airy is a name, not referring to the air, the Airy theory is the overly optimistic prediction. So now we know we're aberration limited. Let's do our first example, the human eye. The diameter of the entrance pupil in the human eye, according to the ophthalmology literature I looked at, ranges between 1.5 and 8 millimeters. So we could figure, and the focal length is, again, the ophthalmology literature has a range of estimates. It's obviously going to depend on the person, the age, yada, yada, but about 20 millimeters. So we can compute tan theta, and then we can compute sine theta. And the spot size would be 0.6 times, let's say, the wavelength of light in the middle of the visible spectrum. It's what you're most sensitive to anyway, divided by sine theta and the refractive index of the vitreous humor, or the vitreous of the eye. And that refractive index is not going to be exactly water, but water is a pretty good estimate. So we're going to get spot sizes between 1.3 microns and 6.6 microns. That, assuming it's all diffraction limited, is comparable to or even smaller than the size of a photoreceptor cell. If you've taken the biophysics class, you've probably learned that bacterial cells tend to be about a micron in diameter, give or take, and animal cells tend to be about 5 to 10 microns in diameter, give or take. There are exceptions. There are some giant bacteria. There are some giant eukaryotic cells. There are some very tiny eukaryotic cells, but as a rough estimate, 6.6 microns would be maybe a small human cell, typically. All right. Now we could ask, what's the size of the aberration limited disk? Well, it turns out that you can often approximate it, and this is just a rule of thumb based on Zemax experience. This is not anything I've derived from a formal theory, but you could approximate it as r cubed over roughly 5 f squared, and that would usually get you within a factor of 2 or 3. And that's just based on my experience playing around in Zemax. I often get numbers roughly like that. So when does the diffraction limit match the aberration limit? Well, let's see. We're going to take 0.6 lambda over n sine theta. We're going to approximate sine theta with tan theta because they're pretty close for this range of values. Tan theta is radius over focal length. So we're going to get the 0.6 lambda focal length over index times radius is radius cubed over 5 focal lengths squared. If we solve for the radius at which these two limits, at which these two cases overlap, at which they both give the same prediction, so that must be the crossover, we get that r is around 1.7 millimeters. And for the human eye, the smallest pupil at the brightest time of day is going to be about 0.75 millimeters in radius. So the human eye sits right on that edge. It sort of makes sense if you think about it, that the human eye would sit between those extremes. Because if the human eye were very much diffraction limited, that would mean that the pupil is too small. You could widen the pupil and get sharper resolution. And you might say, well, won't widening the pupil cause more damage to the eye? Well, we could just evolve to have a lower density of photoreceptors so that we won't absorb as much light and be overwhelmed. There are creatures that are adapted for living in daylight in very bright places. Conversely, if the eye was aberration limited, then you could always narrow it. And while narrowing it, you would improve your resolution. And yes, you would get less light. But again, evolve a higher density of photoreceptors. There are animals adapted for dim light. And so you kind of want to sit right on the edge between those two regimes. Because if you sit on the edge between those two regimes, it means that any change you make is going to make things worse, which means you're kind of at an optimum. And so the human eye sits right on the edge between those two. And then we have a density of photoreceptors that works for our typical conditions. The human eye is really an amazing piece of optical engineering. Any questions? I don't know if I mentioned this before, but really the only way to improve a human eye is, strangely enough, to get old and have cataract surgery. Because when you have cataract surgery, they remove the lens. What happens is that the inner lens gets cloudy. The cells in there are supposed to form transparent layers, but after 60 or 70 years, some things break down. It's no longer transparent. The lens is literally cloudy. It's hard to see through. And so what they do is they take out the lens and they replace it with a new one. And nowadays, the new lenses are not just clearer, but they're actually designed to reduce aberrations. They're really amazing things. So you actually can experience your best vision around the age of 70 if you get cataract surgery. All right, now let's talk about how beams spread out. Let's reverse things. Instead of focusing light to a point, let's have a point source. And of course, ideally, that point source would take rays of light and send them parallel to the axis. But it's going to spread out in all directions because that's what waves do. Or at least it's going to spread out over some range of directions. And if it is spread out by an angle theta, well then this top path and this bottom path differ from each other by an amount a sine theta. And so the largest path difference would be between these two. That's a sine theta. And again, we get destructive interference adding up over all the paths from the surface of a circle if the largest path difference is 1.2 lambda, because then the average path difference is 1/2 lambda. So we get that A sine theta is 1.2 lambda, and sine theta is 1.2 lambda over A. So let's just go with a laser that many of you have lying around a house, or at least you get access to at school, a laser pointer. Beam diameter, roughly 2 millimeters, wavelength, roughly 532 nanometers for my favorite laser pointer. Sine theta is 1.2 times 532 nanometers over 2 millimeters. That's 3.2 times 10 to the minus 4 radians. And if you do the conversion, that's 0.02 degrees. That's tiny. We can treat a laser pointer as producing well-collimated light to a very good approximation. It'll eventually break down, but it's a good approximation for a while. Now we could also ask about the performance of a gigapixel camera. And we're going to run things in reverse. And the way you could think about resolution and running things in reverse is that if this is where the 0 is, okay? If we had a pixel here, light from that pixel would spread out over this range, all right? Yes, there's a little bit of light past this first 0, but it's just a very small percentage. So we could treat that pixel, light from that pixel would spread out over this. And if light can go one way, light can go the other way. So light over this range could be focused down to 1 pixel. So in order to see a detail, the two details would have to be spread out from each other by an angle larger than the arc sine of 1.2 lambda over A. Now, several years ago, I went to a presentation by some people at the USC Film School who had made a gigapixel camera that could resolve a face 3 kilometers away. And it resolved a whole lot of other things. It's a gigapixel camera. So it is 10 to the 4th, something times 10 to the 4th, closer to 10 to the 5th by 10 to the 5th pixels across. It's picking up a whole lot of information. And what I want to do is, if they didn't give us all the technical specs of their camera, but if they can resolve a face 3 kilometers away, well, then we can figure out the aperture of their camera. In order to resolve a human face, in order to make out details, realistically, in order to identify people, you would need at least centimeter resolution to pick out anything. Otherwise, all you could maybe say is skin tone, do they have a mustache or not, something like that. But if you really wanted to pick out details of the person, you need at least a centimeter resolution. So two details, a centimeter apart, 3 kilometers away, are going to produce a very tiny angle. And the tangent of that angle would be 10 to the minus 2 meters, a centimeter, over 3 times 10 to the 3rd meters. And of course, for an angle that tiny, tan theta is theta in radians. So we're going to have that the aperture is, well, this. We're going to have a 20 centimeter aperture. That's a big lens. That is a very big lens. And that is apparently what they use for their gigapixel camera. Any questions? Now, it is claimed that DoD can read your license plate from space, or, yeah, it would be DoD. It would be the National Reconnaissance Office, which is under DoD. So a satellite is going to be maybe 200 kilometers up, and that's 2 times 10 to the 5th meters. And to read a license plate, realistically, you're going to need at least 2 centimeter resolution, at least. I know that in the movies, they just get some blurry image from the camera and then from the satellite, and then someone says, run and enhance. And the geek types something. They say, all right, it's coming. Run and enhance again. And then the tech person types something, and then it all works. But in real life, if you don't have that resolution present to begin with, you're not going to see much. So if we were to figure out what the diameter of their camera would have to be, let's see, we take this angle, Sine theta is roughly tan theta is roughly theta in this regime. And we're going to be optimistic here. We're going to assume that they work with blue light, really tiny wavelengths. Because if they work with small wavelengths in the numerator, then they could have a small aperture size in the denominator. But even in this case, we get a 5-meter aperture. Now, I don't think that they actually have a mirror that's 5 meters. They could. Maybe they have that for some things, but I don't think they have a ton of 5-meter mirrors being used on a daily basis to read license plates. What I suspect they have is 2 smaller meters that are two smaller mirrors that are at least 5 meters apart. They each collect light, and then they combine and interfere their signals. This is done with 2 of the telescopes on top of Mauna Kea, 2 telescopes used for civilian astronomy research in Hawaii. By the way, do you guys know what Mauna Kea is? I'm sure Patrick does going into planetary science, but does anyone else know what Mauna Kea is? Okay, so Mauna Kea is a volcano in Hawaii. It's a very, very, very high mountain. And it's so high up that even though Hawaii is tropical and humid, the air is very, very dry up there. And they get basically no precipitation. And the air is also very thin up there because it is so high up that the atmospheric pressure is lower. And several years ago, I went to Hawaii for a conference on things unrelated to astronomy. But I had some time off in the middle of the conference. And so a buddy and I and a few people we met at the conference rented a Jeep and went up to the top of Mauna Kea. And halfway up, they have a visitor station. And you have to stop there for at least an hour so that your body can get acclimated to the lower to the lower pressure. And we stayed for an hour. We should have stayed for more. Then we drove all the way up to the top of Mauna Kea, and I was definitely feeling dizzy up there. It's very cold. The air is very thin. If you're not adapted, you'll feel dizzy. But it's a great place for doing astronomy. And they have more than a dozen telescopes up there. There's some controversy over that, which we can talk about some other time. But 2 of the telescopes are set up so that their mirrors are always or can be pointed at the same source, which means that they have very good coordination of the controls on the 2 mirrors, so that they're always pointed at the same thing in the sky when you're doing this technique. And then they run a fiber optic cable between them so that they take light from one, they take light from the other. And because the 2 telescopes are separated from each other by a kilometer, give or take, at least a few hundred meters, the light took slightly different amounts of time to arrive at the 2 telescopes, which means that there's a phase difference between the 2 telescopes. And they can take advantage of that phase difference to figure out what angle the light was coming in at, which is just another way of extracting high resolution information. And they get that phase difference by combining the light from the 2 telescopes with a fiber optic cable. And I suspect that the National Reconnaissance Office, rather than sending up a giant fleet of 5-meter or larger mirrors, has probably been doing something like that. Any questions?
How much light do you have to actually collect to be able to...
I can't hear you. Say it again.
How much light would they have to collect for each image to actually be able to resolve that?
It would depend on how bright the source is, which, okay, the thing with light collection is when you ask how much light do you need, the standard answer is how bright is the source, how long can you wait, and is the source moving? Because if it's moving, you can't wait very long. What you would need is realistically, it turns out that the noise in the signal is roughly proportional to the square root of the number of photons detected. So I think that they would want to have, at least 400 photons to get at least 5% accuracy. And then I have intuition for fluorescent fluorescent sources under a microscope. So if we start talking about what you need to do to get 400 photons, I can just immediately start rattling off the names of dyes and lens sizes. But for looking at a license plate from space, I've never done the calculation of solar intensity. We could, you know what? That's a good exercise. Let's do that. We're getting through these notes pretty quickly. Let's do that exercise. I'm going to switch to my other device, share my screen. All right. Telescope on satellite reading license plate. So we've got a license plate here, and we've got some feature on it of size A. We're going to say A is 10 to the minus 2 meters. So the area, big A, is A squared, is 10 to the minus 4 meters squared. Now, sunlight, the intensity is about 10 to the third joules per second per square meter. So P is IA is 0.1 joules per second. Now we have to convert that to photons per second. For a photon, E equals hc over lambda, or h times the frequency. So that's going to be 7, we're doing all of these things to just one significant figure, times 7 times times 10 to the minus 34 joules times seconds, times 3 times 10 to the 8th meters per second, over 5 times 10 to the minus 7 meters. So 7 times 3 is 21 over 5. That's roughly, well, we'll do 4.2 times 10 to the minus 19 joules. All right, so to go from power, joules per second, to photons per second, 0.1 joules per second over 4.2 times 10 to the minus 19 joules per photon. Well, that's going to be 0.1 over 4.2 is going to be 0.025 times 10 to the 19 photons per second, or 2.5 times 10 to the 17 photons per second. But that's what's hitting it. These things are going to, a license plate, it's dirty, it's going to have low albedo. Let's say that, you know, we're only getting 40% of the photons. Okay, so 2.5 times 10 to the 17th photons per second hit the plate. 40%, or 1 times 10 to the 17 photons per second bounce off. All right, so we've got, from that little segment of the plate, we've got 10 to the 17th photons per second. Now, if they were spreading out in all directions, then the number of photons per second would just be number per second over 4 pi r squared if spreading in all directions. But they don't go into the license plate. That's not allowed. So we're going to have that the intensity, that the photons exiting per area per second equals number per second over 2 pi r squared, because they're spreading over a half sphere. Any questions on this so far? Okay. Now, the satellite is roughly 200 kilometers away. All right, so R is 2 times 10 to the 5th meters. So we've got 10 to the 17 photons per second over 6 times 4 times 10 to the 10th meters squared, because 2 pi is roughly 6. All right. And so it's really 6.28. 6.28 times 4. Oh, this is going to work out nicely. 6.28 times 4 is roughly 25. So we're going to have 10 to the 7th photons per second per meter squared over 25, or 0.04 times 10 to the 7th photons per meter squared times second, or 4 times 10 to the 5th. All right, so we want to get, I'm saying, at least 400 photons from that patch, at least. Realistically, we probably want 1,000 photons. Well, we'll say 400, okay? We're going to say 4 times 10 to the second equals 4 times 10 to the 5th per meter squared times second multiplied by A delta T. So we could increase the collection area. We could play with the delta T. Just because things are moving, I think you would probably want 1/10 of a second exposure time. I'm just guesstimating here. There could be reasons. I mean, it all depends on the angle at which you're looking at things to figure out how far it's crossing your field of view. But let's just guess that they want to do 1/10 of a second exposure. So that's going to make this 10 to the 4th. All right, the 4s cancel. And I'm left with A equals 10 to the minus 2 meters squared, which frankly sounds low. I feel like I've done something wrong here. I know I didn't do anything wrong in these conversions because this is a few electron volts. The energy of the photon is a few electron volts. That is indeed correct. Does anybody see an arithmetic error on here? I'm not seeing it either. So maybe they want way more than 400 photons. But then again, thinking about the images that I have seen, that's actually a pretty large pixel to manufacture. So they probably have a couple of pixels there. But then again, no, that's not a pixel area. That's the entire detector area. That's the area of the entire detector. So that means that they want 10 centimeters by 10 centimeters. Okay, 10 centimeters by 10 centimeters is not completely insane. I still think it's low. There's just something that's bugging me about that, but this is not a field I've worked in. So all I can say is that they probably want of order 10 centimeters by 10 centimeters. And the more I think about the quantum optics of it, the more I'm convinced that they probably want more like 4 times 10 to the third photons. They probably want at least 10 times more photons. So if they want 10 times more photons, then we're going to have to multiply area by 10. And so size by square root of 10, which is roughly 3. So 30 centimeters by 30 centimeters. That actually does not surprise me too much. It doesn't surprise me that 30 centimeters could collect enough light. The problem is that they would need to have these two things separated more by 5 meters at least. That way they could tell the reason to have it separated by 5 meters is just so that this difference over here, this path difference, so that path difference would be large. And that way they could tell the difference in phase and they could resolve the fine details. Now, this is all just a very crude estimate. If you interview at a defense contractor and they look at you funny, well, you know, this was my first guess. My first guess was probably not completely correct for the same reason that when they make one of these satellites, I'm pretty sure that whatever they manufacture is not based on their first design meeting, but on many, many design meetings. But this is a starting point for the reasoning. I would think that 30 centimeters might plausibly collect enough light, but they would need to be separated by a longer baseline. Any questions? Anyone? All right, then let's go back to what we were doing. Another example. Cal State San Bernardino has a telescope. The last time I read about it, heard about it, they had a 20-inch or roughly half-meter mirror. I don't know, maybe they've upgraded since then. But with a half-meter mirror, let's figure out how large or how small of a feature you could see on the moon. The moon is about 3 times 10 to the 8th meters away. And so the angular size of an object, if this object has size x, the angular size would be x over 3 times 10 to the 8th, which would be 1.2 lambda over the diameter. So you would get 360 meters for this feature size. So with a half-meter telescope, you would not be able to watch the moon landing. All that you would have seen with the moon landing and all that you'll see in some future moon landing, if NASA really does go back to the moon, is you would see a bright spot. You would see the flare from the thrusters firing to slow the descent. But you would just see that flash of light. You would not see any details of it. You certainly wouldn't see a person stepping out of the moon lander and announcing, this is another small step for a man or woman and another giant leap for mankind. You wouldn't be able to see any of that. Even if you did have the geek from some spy show saying, run enhance. All right, let's talk a little bit about where these patterns come from. If we were to try to calculate this, so we've got a circular aperture, we've got coordinates little x, little y in the plane of the aperture. We've got a detector. We've got coordinates big X and big Y in the plane of the detector. But since everything is circularly symmetric, if I find the diffracted field along this line, I also know the diffracted field along that line or any other line. So we're just going to find the diffracted field along this line. And we established before, last time, that the field is an integral over the aperture of e to the I kx times x in this plane plus ky times y in this plane. And if you're wondering, well, where does the coordinate big Y go in? Big Y determines theta. The further away from the center of the detector we are, the larger theta. And the larger theta is, the larger ky is. And since we're only looking at things that travel along, that fall somewhere along this line on the detector, we're only looking at k vectors that have non-zero y and z components, but we're assuming that the x component of the k vector is 0 because we're not worried about lateral deflections in the plane. So k is just k sine theta y hat plus k cosine theta z hat. And the r vector in the object plane is x times x hat plus y times y hat plus 0 times z hat. So k dot r is k times y times sine of theta. And now if we're going to do this integral over this plane, because we're doing the integral within a circle, it's easier if we start working in polar coordinates in the plane of the object. So we're going to say that r is the distance from the center of the aperture, phi is the angle in the aperture plane, and k dot r is kr sine theta sine phi. So we set up that integral. We've got this exponential, which might look at first like something you could do, except remember, it's got this sine phi. We've done plenty of e to the I kx dx integrals. We've never done e to the I k times sine of x dx or k times sine of phi d phi. We've also got this r dr. That just comes from finding the area in polar coordinates. And now I make an assertion. I make the assertion that this angular integral, the integral over phi, has a name, and that name is the Bessel function of order 0. Back in the 19th century, the way that you got your name into a math textbook was that you studied some integral that had, or you studied a family of integrals, and you worked out the properties of that family of integrals, and then they went into a textbook and you got those integrals named after you. So we've got Bessel functions, we've got Hankel functions, we've got Legendre functions, Laguerre functions, Airy functions, you name it. All right, this is called a Bessel function. They may have covered it in math methods near the end of the semester, maybe not. If they did, it would have been near the end of the semester. So we've got the integral of a Bessel function, because all we've done so far is the integral over phi. Still have to do the integral over r. Now it turns out that the integral of a Bessel function of order 0 is another type of Bessel function, a Bessel function of order 1. And it looks like this. And all that matters for our purposes is that this integral is a function that we can look up. It may seem kind of weird to just say, hey, here's a function we can look up. We don't really know anything else about it. But think about sines and cosines when you were first introduced to them. By now, you've worked with them for years. You've got some intuition for them. But when you were first introduced to them, you were told, okay, here's what the sine of an angle is. Well, how do we get a number out? You plug it into a sine function. And if you were in my generation, you were told, well, when we let you use your calculator, you plug it into a sine function. But otherwise, you look it up in a table in the back of the book. And if you're from an earlier generation than that, there was only the table in the back of the book. So it's just this number you looked up. Whether you looked it up on a computer, which is all that it really comes down to when you plug it into Mathematica, or you look it up in a book, it's just this number from a table. It's the same thing for Bessel functions. So let's go back to Mathematica. Let's go back to the diffraction pattern of a circle. And we can plot this for different, why is that not working? We can plot this for different values of the aperture width. What I want you to notice is that this is, in technical terms, freaking tiny, okay? This is a really, really narrow plot. You have to pick a very, very small value of a very small aperture to see anything at any sort of angle that we could begin to measure. So I'm going to change theta max range. Instead of going from 0.01 to 90, I'm going to have it go from 0.001 to 1. And then we can make a little bit bigger, right? But it is really tiny. Now, where it gets more interesting is if instead of putting this all in terms of K, A, and sine theta, let's just plot this as is. And we'll plot it against the Gaussian. All right, we'll plot it. Well, actually, let's not even do that. Let's just plot the Airy PSF by its own. Let's make it a little bit wider than that. All right, you see how it has a peak, a node, a secondary peak. If you squint, you can persuade yourself that maybe there's a third peak. We could always change our plot range to verify that third peak. Let's go from 0 to 0.1. Yeah, there's a third peak there. Now let's try to figure out where this 0 is so we can make that 1.2 a little more understandable, okay? I've just been asserting that 0.2 for a while. Let's zoom in on this range. This is 1, 2, 3. So somewhere between 3 and 4. Let's do probably closer to 4. So let's go from 3.5 to 4.5. All right. And we'll do an automatic plot range for now. All right, let's zoom in. It's somewhere between 3.7 and 3.9. It's somewhere between 3.8 and 3.85. All right, so it's right around 3.83. We'll get even a little more precise just to be careful. Oh, yeah, so somewhere between 3.830 and 3.835. Looks like it's going to be around 3.83 something. We're not going to worry about it too much more. So if we do that, go and work this out by hand. All right, we know that we get a 0 when Ka sine theta equals 3.83, give or take. So that's, 2 pi over lambda A sine theta equals 3.83. And I feel like I'm leaving something out at this point. Feel like something is wrong, but we'll deal with that later. Okay, 3 point, which, oh no, that's okay. So if we divide both sides by pi, we're going to get 2a sine theta over lambda equals 3.83 over 3.14. And I know that this is 1.2. And now I'm trying to figure out where the 2 went. And I think where the 2 went is, I did that to a over 2. All right, so I think it should be Ka over 2 sine theta.
You're right, because R is A over 2 and it was K dot R.
Yeah. All right. So that's where all of this comes from. It comes from doing the integral. And yeah, in order to do that integral, I still have to make some assertions. But in the end, there are always assertions. At least I'm taking you a step deeper into the assertions. Questions about any of that? Anything at all? Then let's go into Zmax. All right, I'm going to start sharing this screen again. Let's go look at that microscope objective that I showed you last time. Take this a minute to open. All right. So let's look at no, I meant to look at a Psf cross-section, not a cross-section of the system. So we'll go to Psf, Huygens Psf cross-section. All right, now one thing we could ask is this in the right place? Okay, we said before that we should get a 0 when y equals 0.6 lambda over the numerical aperture. So let's just take a look. Our wavelength was 780 nanometers. And let's try to figure out our numerical aperture. If we zoom in over here, to me, it looks like our numerical aperture is, I'm gonna have to write some things. I'm gonna save some data over here, all right? So now, lambda equals 0.78. Theta would be the arctangent of, if I go over here, This distance, let's see, delta y over delta x. So delta y would be from, here's a vertical coordinate of 0 to 0.49, give or take. And then, well, let's see, our horizontal coordinate here is 45.9, and, oh wait, this is 0, that's 0.37, okay, because this was off axis, so I should be working here. This is from 0 to 0.37, and this would be from 0.49 to 0.5.
You're using the green one for the horizontal again.
I know, I'm just checking to try to figure out. So here I get 0 to 0.4. It's very confusing. Let's really zoom in on the blue so I can get it accurately. Okay, here the blue coordinate is 0.37, and here it is indeed 0. And then the horizontal coordinate, this is about 45.8. And this is 46. Maybe, yeah, so 45, let's say 46.06 minus 45.86. Okay, and then the resolution should be 0.6 times lambda divided by sine of theta. And I get 0.53 microns. And we know those units are microns because the units of the wavelength are microns. When I go here, I get a node at 0.51 microns. And keeping in mind that my angle estimates were not perfect, but also keeping in mind that, do you see perfect destructive interference here? I don't. I don't see this going to 0. This lens has some aberrations, right? It doesn't have a lot of aberrations, but it has some. Let's find that minimum a little more accurately. Yeah, it's still not 0.53, but this lens has some aberrations. We know that because this isn't near 0. We could ask, well, maybe it's because all of this is choppy. There's an easy way to check that. It's going to take a little more time. Yeah, and even factoring in, even when we go to higher resolution, well, now we get at more like 0.53. So yeah, it's very close. Depends on how choppy this is. It also depends on how good our measurement of the angle was. And of course, we know that this shouldn't be perfect anyway, but it's a pretty good theory. Any questions on what I did there? Let's compare it with a Gaussian. I don't know of a way to plot a Gaussian in Zmax. So what I would do is I would just copy all of this. It's going to be an easier way. Copy. paste it into Excel. And then we're going to do a Gaussian, but we don't know. It's going to be e to the minus something. But we don't know what that something should be. So we're going to start by guessing that that something is 1, and then we're going to change it. And if you just tell it to do that, well then, as we paste down, we're going to hit a problem. So we're going to tell it F2. Those dollar signs in Excel mean that when I go to the next row, well here, let me just type out the whole formula, and then I'll explain what this does. When I paste down like that, when I drag a formula down, let's make a change. You go down here, and instead of using the value of y from this column, it's now using, well, it's using the value from this column. Instead of using the value from the row way up there, it's using the value in B253, okay, because I'm on row 253. But for that first number, because I put those dollar signs in, I said, hey, when I drag it, don't change that row. Anything that I don't put a dollar sign on, when I drag, it changes the row. Anything that I do put a dollar sign on, when I drag, it doesn't change the row. So now I've got these two expressions next to each other, all right? And with these two expressions next to each other, oh, wait, you know what I didn't do? I didn't normalize. I didn't fix that maximum to be 1. So we're going to have a little bit of mismatch if I don't update that. All right, so now let's try it again. We copy, we paste. Got to redo that pasting. Some labeling, Y, microns, Zmax, Gaussian approximation. All right, now in order to compare these things, we're going to first plot what Zmax gave us. So we just do insert, XY scatter plot. Then we select data. We're going to add another data series. The X values will be...
Just hit edit rather than add.
Oh, my bad. Add. Okay, so we're going to get the X values from here. Thank you. We're going to get the Y values from the other column. We go up, and what on earth did I do? B51 to B258. Those are B1 to B258, D1 to D258, okay. Zmax, edit B2 to B258. Do this a million. What?
One includes the column headings. I'm not sure if it matters, but you know, these things are finicky.
Yeah, could be. Let's try that. There's absolutely no reason why that should work, and yet it did. Okay, Excel. All right, let's format this axis range just so that we axis options. Okay, I have no idea why it's going from 0 to 250. I have absolutely no idea why that is, but I'm beyond the point of caring. So we're just going to take this from 50 to 200 and we're just going to roll with it. And then we're just going to play with the value of that constant. All right, when I made this constant 1, I got something that's too wide. So if I want to narrow it, should I make that constant larger or smaller?
Smaller?
Well, if I make it
Actually,
smaller,
sorry, larger.
Smaller number, yeah. If I make it smaller, I'm taking e to a smaller number, e to the minus a smaller number. E to the minus a small number does not decay very rapidly, whereas e to the minus a large number decays very rapidly. So I'm getting closer. That's pretty good fit. That's even better. That's better still.
They're still here.
We can debate which of these. You can see that this is excellent overlap over here, a little bit underlap over there. You know, it's going to be somewhere around 13 or whatever. But the point I want you to take away is that we can actually take the Zmax output and fit it to a Gaussian really well. And that matters because if you were just showing someone a graph and saying, look, here's the graph, we're done. If you had to start doing some calculations like, okay, you know, how is the intensity going to typically vary as you go this far from the center? And if you ever have to do a hand calculation, doing hand calculations with a Gaussian is easier than most of the alternatives. And so people will fit Gaussians to these kinds of curves all the time. And it's not just a rough rule of thumb. There are people who literally won the Nobel Prize for work on fitting to Gaussian. Not that they won the whole Nobel Prize just for fitting to Gaussians, but the point is, someone's got their microphone on. So I'm overhearing another conversation.
Yesterday and I gargle and my pain went away.
It's a fascinating conversation, but
she's gonna laugh at me.
we need to get through some Zmax stuff.
I told you.
So why can't I see all the participants?
And it is like so nice.
Do you want us to name them off for you?
Okay, now it seems like everyone's muted. All right, we'll leave it alone. All right, now people have done incredibly high precision work on things like this using the Gaussian approximation the whole time. And the results that they got were accurate enough that they literally won the Nobel Prize for it. Now, obviously, they did a lot more than fit Gaussians to things. But the point is that the Gaussian approximation is so good for these kinds of curves that some of the most precise work out there makes use of it, and it still does fine. Anything else I want to say in there? I guess the only thing I would add is that people have found via trial and error that the best approximation is 0.27 times k squared over the numerical aperture squared. If you take e to the minus 0.27 k squared y squared over numerical aperture squared, you get a pretty good estimate. And I think at this point, I've already gone for an hour, more than an hour, and we've got Zmax out. And so I just want to ask, have people tried inserting the tube lens into this lens system yet?
No, was working on the long problem set.
Does anybody have questions about it? Does anybody want to play with it? I'm not going to do all of the work for you, but I will show you what I got when I inserted it. So what you should get is pretty much something that looks like this if you do it right. You're going to have the tube lens, which is much larger than the objective lens, and that's okay. There's nothing that would stop a person from manufacturing a smaller version of this if they wanted to. So you're going to have the tube lens, and then about a centimeter away, you're going to have everything that we had before. And if this tube lens was well designed, if Adrian Negrian did things right, then you should get almost the same performance with the tube lens in place that you would get without the tube lens in place. Any questions? All right, I'll just say a little more. I'll give you an overview of the first part of next class. What we're going to do next time is we're going to finish talking about focused beams. We're just going to note that in principle, of course, the focused beam, well, everything would come to a point. It doesn't. And so you could kind of think of the profile of the beam as being like a hyperbola. All right? With a hyperbola, out far away from the middle, a hyperbola almost looks like a pair of lines. Okay, and so we see that the path of the waves is almost following these lines, these asymptotes. But near the center of the hyperbola, they never get closer than a certain fixed distance. And a hyperbola is actually an amazingly good approximation for a focused light beam. It's not a perfect approximation. There are people who could quibble with it, but laser designers have gotten a long way in a very profitable field, usually using a hyperbolic approximation, at least to start their calculations. So next time we'll go over that. We'll talk about the minimum width, how the minimum width that they get relates to what we did before. We'll talk about the fact that, well, you know, you can go a certain distance away from the center before it starts to get significantly wider and starts to look more like the asymptotes than like this curved region down here. And we'll fit all of that into a Gaussian approximation. And then once we're done with that, we're going to start talking about another feature of Zmax, something called a modulation transfer function, which is what people use all the time to characterize an instrument. In fact, it's one of the things that people in metrology labs routinely talk about when they're shipping optics projects. There are people who graduate from this department who spend a certain amount of their day measuring modulation transfer functions of a piece of equipment before shipping it. There's a company, were any of you at the alumni panel last month? I think a few of you were. And there's a guy named Jason Ossel who graduated from here a few years ago and is already in management at a company called Supply Chain Optics. And basically, what Supply Chain Optics does is they talk to customers who need optical components but don't know all of the manufacturers, particularly the niche manufacturers. The big famous manufacturers with their catalogs, there are some exceptions, but for the most part, their quality control is a known quantity. There are niche manufacturers that, they might make one of the pieces you need for the system, but not the entire system. Or sometimes they are in countries where the manufacturing is cheaper and the quality control is getting good, but this company acts as a middleman to guarantee the quality control, to basically do their own check on the instrument before they ship it to the customer. So they're a middleman who's adding value via quality control. And they measure modulation transfer functions. As a matter of fact, adding modulation transfer function to this class, which is what we're going to do next time, and it's a feature in ZMAX, is something added specifically at the urging of people who have worked in roles like that. So at this point, I'm not going to say any more. I'm going to give you the rest of the time to work in ZMAX. I'll be logged in for as long as other people are logged in, and if you want, you can do a screen share with me if you have questions about adding the lens. Have as good of a break as you can have while stuck at home, and take care. See you in a week and a half. I always end this class about a half hour before the official end time to give them time to do their project. So I'm still logged in. If people have questions, they're going to be asking me.
Hey, Dr. Small.
Yeah,
Are you going to be answering emails over spring break?
absolutely.
Okay, thank you.
You're welcome.
Oh, Professor, I actually had a quick question.
Sure.
It's sort of outside the class. When it comes to like two-photon microscopy,
Uh-huh.
know that two photons to be absorbed by some fluorophore at the same time.
Yeah.
Does what we've learned today sort of give insight as to why they don't have like 3-photon microscopy or more, or do they have that?
They do have 3-photon microscopy. It's a big deal in neuroscience.
So why? So if you could get a smaller excitation volume for fluorescence with more and more photons,
Yeah.
what's like the problem? Like, why don't people just use more and more photons?
Why don't they use more and more photons in 3-photon microscopy?
No. I mean, why don't they have techniques where they use 4 photons or 5 photons?
Oh, because every time you increase the number of, in order to get several photons absorbed at once, you need several photons in the same place at the same time, which means you need very intense pulses. Now, there's 2 ways to turn up the intensity. One is to turn up the power, except that you will very quickly run into some pretty dangerous levels of power and overheat the laser. The other is to take a small amount of power, but compress it, a small amount of energy, and compress it into a short amount of time. So they use femtosecond pulses. That way, the actual power coming out could still be just a few hundred milliwatts, but those few hundred milliwatts, that's the total power over a second. But that few hundred milliwatts does not come as 1 milliwatt in the first hundredth of a second, another milliwatt in the second hundredth of a second. Instead, or sorry, another 1 millijoule in the first hundredth of a second, another millijoule in the second hundredth of a second. Instead, it could come in the form of a millijoule compressed into 10 to the minus 15 seconds.
I see. Okay.
And so in order to go from 3-photon to 4 to 5, etc., they would have to shorten that time even more. But you can't make these pulses much less than a femtosecond. And so 2-photon microscopy is basically an off-the-shelf turnkey apparatus that doesn't require nearly as much specialist attention as it used to. 3-photon microscopy is or soon will be at that stage. I don't know if 4-photon microscopy will take off because 2 and 3-photon microscopy are already so good. 4-photon microscopy might take off for niche applications, but 5-photon microscopy, in order to be useful, they would need new power sources and new laser pulse concepts that aren't even on the horizon as far as I know.
Okay, I see. So for 5-photon microscopy, we're going to need 5 photons hitting at the same time, and that's going to require new technology. Okay.
Basically, because you're either going to need to crank up the power, or you're going to have to either put more energy into the same time frame, or put the same amount of energy into a shorter time frame.
Right. Okay. I guess I just have a general question about 2-photon microscopy then.
Yeah.
I'd like, because I was reading some papers and they were saying that eventually you approach like a diffraction limited volume.
Mm-hmm.
And so I guess I just have some things flying around in my head after today's lecture, but I can't put some questions like into words.
Okay, so what happens is you're never going to make the volume of the region. The region in which you've got a high light intensity is always going to be roughly the cube of the diffraction limited spot size. All right? There are ways to make it maybe half of that, but you're always going to be working with something roughly that volume. So the area is always going to be roughly the square of the diffraction limited spot size. So you need high intensity. That's power per area per time. Yep. You can make the area small, but you can only make it so small. You can make it about as small as the diffraction limit and not much beyond that.
Mm-hmm.
The time, you can make about a femtosecond, not much shorter than that, at least with the technologies as we currently understand them. And so then all that leaves is cranking up the power But as you crank up the power, the energy flowing through the system, basically your laser could overheat. That's a very real danger. I mean, I haven't done a lot of work with pulsed lasers, but I've worked with other kinds of lasers where you have to run some pretty heavy cooling water through the apparatus, or the thing could literally destroy itself.
Okay, I see. That's really interesting. I didn't know that was like the bottleneck.
Yeah, all lasers need cooling. Some of them need much more cooling than others. I mean, all lasers generate waste heat. Everything generates waste heat. The laser point
Sure.
waste heat is negligible. For the Heaney lasers that we use in demonstrations, it's just some careful design of the packaging to enable internal airflow and internal conduction. For more powerful lasers, you can need a cooling water supply. For pulsed lasers, the whole trick is to avoid running huge amounts of energy through there by taking a modest amount of energy and compressing it to a small area and a small amount of time. Diffraction limits the area that you can compress it to.
Right.
And what time you can compress it to, the period of oscillation for visible light is going to be the time it takes to travel one wavelength. So it's going to be about 5 times 10 to the minus 7 meters divided by 3 times 10 to the 8th. So you're going to get a femtosecond.
Right.
And so you can't make it any shorter than a few femtoseconds. And actually, it's going to be even worse with the infrared light that you would have to use for multiphoton excitation, because the wavelength will be longer.
I see. Well, from what I was reading, that longer wavelength is helpful for imaging biological tissue because,
Yes.
yeah, okay, it can like penetrate deeper. There's less absorption.
Less absorption and also less scattering.
Because you have
Basically,
1 over lambda to the 4th or something, right?
for Rayleigh scattering, not all scattering is Rayleigh scattering, but yeah.
Right, okay.
And the way to think about that is that radio waves pass through us for a couple of reasons. One reason why radio waves pass through us undistorted is simply that we are very small compared with the wavelength of the radio wave, so we scatter weakly. A cell is scattering light, and so infrared light, the cell is going to be, well, the cell is going to be comparable to the size of the light, but for visible light, the cell is larger than the visible light, so it scatters a lot. For infrared light, the cell is often comparable to the light, the wavelength of light. It doesn't scatter as much. And the key features of the cell that actually do a lot of the scattering are even smaller compared with that wavelength. So,
okay, that makes it better. Yeah.
yeah. So infrared light is great for deep brain imaging in mice. And it's even used, I don't know the status of this, but I know people who have worked on using infrared light to see through the human skull to at least look at the surface of the brain for evaluating head trauma.
That's interesting. I was reading that they could image like a couple millimeters in, so.
Into the human brain or a mouse brain?
I believe it was the mouse brain. A team at Berkeley just released a video a couple days ago.
Yeah, what they do is they remove a section of the skull. They anesthetize the mouse. They remove a section of the skull. You can actually have during brain surgery, they remove part of the skull, and then sometimes they actually wake the person up and ask them to perform certain mental tasks to make sure that whatever they're cutting in the brain is not impairing their cognitive function.
Interesting.
So you can do the same with a mouse. You can remove a part of the mouse's skull, have it under some anesthesia, local anesthesia, so that it doesn't feel pain. Then what they do is they attach a bunch of probes to the open part of the skull to image the brain. And then they have the mouse run around with these probes attached to it, and they image it while it's running around and doing things. So you're actually watching a mammal you're watching the brain of a mammal while it's engaging in motor function, while it's engaging in sensory function. And you learn a lot more about the mammal doing that than you could in other circumstances.
That's incredible.
Someday we don't know what they're gonna cure. We don't know if they're gonna cure Alzheimer's or brain cancer or bipolar disorder or what, but someday they're gonna cure something because of that.
Right, and this is what you were talking about by imaging one point of light at a time using.
Yeah.
Right, and so from what I've been reading, they can do 3D scans because you can just have the light focus at a different length. You know, you can just project those 2D scans like upward or downward. It's really cool.
Yep, because it's only the point where the light comes to a focus that the intensity is high enough to produce a 2-photon or 3-photon signal.
Right. Oh man, I thought it was so clever when I was reading about it. Jesus. Yeah.
You know, if you really want to work on things like that, you should either work at a company that acts as a supplier for those people, or you should enroll in a graduate program in biomedical engineering.
Yeah, it's definitely something to consider, because like this is the type of stuff I actually like look up on my own time. I'm like, wow, that's kind of cool.
If this is the stuff you look up on your own time and you like some aspect of the doing the work, whether it's the design or the hands-on part or the programming, if there's some aspect of the work that you would actually like to do and you like to read about it, then yes, that is what you should do.
Definitely. I wasn't expecting this at the end of this conversation, but I appreciate the direction.
No problem.
All right, well, thank you. Thanks for answering those questions for me.
By the way, the company, did you ever hear from the company that I sent this resume to?
I have not heard anything back in my email. So.
You know, the whole private sector is kind of shut down right now, so I wouldn't sweat it too much.
Okay. All right, but I'll definitely, keep my eyes open on my email.
All right.
All right. Well, thank you so much. Have a good rest of your break.
Thank you. You too. Nick, do you have any questions? All right, hearing no questions, I am going to end this session, but as always, I'm available by email and we can Zoom when needed.